relevance. And all right, so at this stage, everybody should be through chapters 1 through 3 and hopefully through chapter 4 and into chapter 5. So one of the purposes of these meetings every week is just to kind of keep people motivated, keep people focused on not waiting until the last week and then trying to cram 46 hours of study into a 40-hour week and then get ready to take the hands-on in the exam. So anybody have any questions from these chapters specifically that you'd like answered, or something you found curious, or anything to bring up for the good of the cause on that? Nope, everybody's being quiet. What about the basic electricity? How much electrical background? I know Ed was telling me he's done a fair amount of electrical work. Are any of you guys, this is all brand new, total novices to electricity? What's an amp? What's a watt? You know, that kind of thing. So, okay, so at least Graham is admitting to the fact that.
Jay, I have a couple one. So specifically I was looking at the diagrams. If you go to chapter 3, page 51, and then all of a sudden the video stops because everybody goes, no, I'm just kidding. The diagrams on the standalone and the grid interactive systems, they show the charge controller between the PV array and the battery bank.
Correct.
Now, if the battery bank is full, then it is my understanding that the charge controller either stops or backs off from giving, charge in there. But the diagrams show that the battery bank is then connected up into the inverter and then into the grid, where that's where you get your credits and get your selling your electricity back into the grid. Well, if the charge controller is throttling or cutting that off, aren't you wasting your potential capacity to sell electricity into the grid according to that diagram?
Yeah, the way that it currently works, and you're talking about like an AC coupled or a DC coupled system that is has batteries but is also connected to the grid. And the way they're currently designed to work is the charge controller will check the state of charge of the battery bank. And if it needs power, it will direct power to the battery bank. And if there are loads to be serviced and the solar array is producing more power than is needed at that moment to charge the batteries, it will also direct power to the loads. Once the battery bank is full, then typically your system will work like it's a grid-tied system, where it will take the excess power that's being generated from the array and it will then divert that not to the battery bank because that's full, but will divert it to the load. And if there is additional power available, we'll divert that to the grid. So it's functioning just like a regular grid-tied array. You're going to service the loads first. Then if there's excess power, it's going to go onto the grid and you'll get credit for that. But it is not designed to then discharge the battery to the grid. The battery is just full and then just sits there until it's needed. The only time in an AC coupled or a DC coupled system that the batteries are being used is if the grid goes down, because typically, now again, I'm saying this and I'm going to be wrong when I say it because you can program these things to get around this, but the batteries are there just in case of emergency. If you're using your battery bank as like a UPS, a backup in case the grid goes down. Now, there's some other options for using your batteries that can be programmed in. For instance, a lot of utilities now have what they call time of day pricing. And so they will charge you different rates for your power based on the time of day. because it costs them different amounts to generate power at different times of day based on load demand. So folks are using batteries to do what's referred to as like load shifting, where let's say that the cost of solar in mid-afternoon or the cost of electricity from the grid at mid-afternoon is, let's say, 20 cents a kilowatt hour. And then in the early evening, it jumps up from 5 in the evening until 10 in the evening. The cost from the grid is 60 cents a kilowatt hour, because that's their peak load demand time. Well, then you can use your batteries to service the loads during that peak cost period, and then recharge the battery either from the grid or from your solar array at a later time. So what you're doing is you're shifting the load. So you charge your batteries in the middle of the afternoon when you have sun, use the battery in the evening when electricity is expensive, and then set it to recharge it the next day when the sun comes up. So that's a fairly typical way you can now power. But you're not going to take the power from your battery and send it to the grid, because you're never going to make anything off of that. It's there to service loads.
Well, Jay, if I just load up those batteries and put them in my Nissan and drive up to the $2 an hour or $2 per kilowatt hour device that you talked about in the last session, then I can get $2 per kilowatt hour by loading those batteries up, right?
Yes. In fact, in California, that's exactly what they're looking to do. In fact, they just announced that they were able to generate up to 900 megawatts of power from batteries stored in homes during the recent heat wave. So what the grid does is they go out there and they say, okay, there's a there's a energy emergency. You know, we're going to experience very high temperatures this week. So we anticipate between the hours of, say, 2 in the afternoon till 6 at night. And typically what they've done in the past is they send notices telling people to cut back on their electric use during that period of time. Now what they're going to do is they're going to say, all right, we're going to send a signal out, and this is a frequency signal that's over the electric lines, to tell those people who have signed up for this, if you'll export power back to the grid during this period of time, we will pay you $2 a kilowatt hour for that power. So in an instance like that, if you've got your Nissan Leaf sitting there in the garage and it's fully charged, then if you've linked in and programmed everything properly, when California Grid says we need power, it'll draw from your Nissan Leaf and pay you $2 a kilowatt hour for that power. Then when the emergency is over, you could just recharge it from the grid and pay them 20 cents a kilowatt hour or whatever it is at that period of time. And so some people are looking at that where you could make money from your vehicle, your electric vehicle, without ever, having it leave your garage. So, that's all fine and dandy when you've got one vehicle, but if you've got 100 million vehicles all connected up to the grid, now you've got an amazing virtual power plant that's out there and with energy that's available. Yeah, Ed, you had a question?
Yeah, won't you be wearing out your batteries doing that? And the cost of replacing the batteries isn't really going to equate to $2 a kilowatt.
Possibly, yes, that's an issue. Will it be $2? No, probably not. I mean, you're going to make some money off of it, but there will be wear and tear on the vehicle's batteries. The other issue that has been a real concern is your warranty on that electric vehicle is based on miles driven, typically, and they equate that. So they might guarantee it for, say, 50,000 miles or whatever. Well, if you're just parking it and charging it and discharging it and charging it and discharging it, then the manufacturer of that vehicle will say, well, you've just voided the warranty, because that's not what this thing was designed to be doing. Right. So they've just recently published a standard, I think it's UL 9740, that says if you use a bidirectional charger that is adheres to this standard, then the warranties should be fine. And they're trying to get buy-in from all the different manufacturers, because what they're trying to get to is a vehicle to grid infrastructure where this can be a thing, and as you're pointing out, if you did this every day, all day long, it's not perhaps the most cost-effective way of dealing with the issue. But if it's there for grid emergencies, then it's a thing. Then it's because the power goes out. They're already advertising the Ford Lightning. It's a pickup truck that's fully electric. It has a 96 kilowatt hour battery in it, which basically, when you looked at the load assessment, the average US home is about 900 kilowatt hours per month. So a 90 kilowatt hour or 96 kilowatt hour battery will provide 3 days of the average home's electrical needs. So you could hook up your Ford Lightning to the charging station, and if the power goes out, you can run your home without turning anything off for a period of 3 days, just off the battery from your pickup truck. And that's already a thing. That's already built into the whole idea of the Ford Lightning. They're also advertising it as a work vehicle where you go out onto the field, and this vehicle has like 6 or 8 duplex outlets built into it. And you plug in your chop saw, you plug in your lighting, you plug in whatever you want to plug into. It's a traveling generator. So that is what they refer to as vehicle to everything, which is, vehicle to load. It's out there being a load generator. That's kind of pointing out the current kind of, what would be a good analogy, like VHS, versus Blu-ray or whatever. Do you put the inverter on the vehicle, or do you put the inverter in the charging station? So that's kind of what the industry is struggling with at the moment. If you want to use your vehicle as a mobile generator and run loads from the vehicle, then the inverter's got to be on the vehicle somewhere, because now you're converting the DC of the battery bank into AC for use. But if you're simply charging and discharging through the charging station, then you can take AC power, convert it to DC in the charging station, and then charge your vehicle, and then take the DC power from the vehicle into the charging station and rectify it into or invert it into AC, and then use it on the loads. Or export it back to the grid. So that's the debate at the moment. Is the inversion going to take place in the vehicle, or is it going to take place in the charging station? So two different philosophies. I personally think it's going to be in the vehicle myself, at which point the charging station is nothing more than an extension cord. You're just plugging your car in and letting all of the conversion of power from AC to DC and back again happen in the vehicle. Just gives you a lot more flexibility, so.
I had, I think, a couple questions on the chapter 4 for this week. And also with what we were just talking about, I've been looking at the Rivian trucks too, and I'm very interested in their vehicle. A little more pricey than the Lightning, and they are a new company too, so they don't have the infrastructure to kind of fill the demand yet. And they've also signed on to, I think, a third of their production is going towards Amazon fleet vehicles.
Yeah.
As they start to produce too, so that'll take away from it. But anyway, I'm very interested in that world at the moment. And so I apologize, but I think my questions are going to be a little bit more pedestrian, as I sort of admitted to my lack of knowledge.
Well, that's the reason we're here.
All right, great. So I finally got like a trick in my head for volts and amps and watts and all that, where the amps is the amount, AA. So like that's the amount that's coming through, and then the volts is the strength at which it goes through.
Yeah, it's the water analogy is a good analogy for electricity, where the amps is going to be the size of the pipe,
Right.
and the volts is the pressure, the water pressure,
Right.
and then the watts is the amount of water that's going through. It's just a combination of the two. How big is the pipe and under what pressure is it being forced through?
Right. Gotcha. And so now that I kind of got that one under my belt, I was wondering if there's anything that like, is an explanation or could be a sort of a trick for the series versus parallel circuits, because I get that one increases one and one increases the other, and that parallel is negative to negative, positive to positive, and the other way around for series.
I've got a little trick that might help you there.
Okay.
Which, because in a lot of ways, basically what you're saying is if you hook it up in series, volts increase, amps remain the same. If you hook it up in parallel, amps increase, but volts remain the same. So the only trick I've ever come up with is there's no A in series, but there's an A in parallel.
Okay. Yeah. Okay.
So parallel.
Thank you. That's all I needed. Yeah, it's another A to A one. That's perfect.
There you
nice. Go. Perfect. And I did have, I guess, one more thing that I'm just struggling with a little bit. I think I might get it, but the phases, the single phase and split phase. So it's coming from the wires to the house in a single phase at 240 volts for the most part.
Right.
And then it splits when it gets into the house.
Yeah, you could think of it as basically when it's coming in, it comes in with two hot wires, each of those wires carrying 120 volts. And then there's also a neutral. So it's single phase power. When you hook up both of those hots to the main, you're getting 240 volts of power. It's still single phase, but in the service panel, it's split. When you look down the line, both of those bus bars, they sort of interweave with each other. But if you put a single breaker in there, you're only drawing off of one of those wires. So you're going to get 120 volts, 120 volts. But if you put a I've just lost the word, but a double pole breaker, you're going to get 240. Now, three phase is a whole different world. Three phase power is well, let me think how, let me grab my whiteboard here.
Great.
Got the whiteboard, but I've also got the screwdriver, which is not going to draw on this whiteboard very easily. There we go. Okay. So, yeah, with the single phase, you're getting two hots, but they're going to be 180 degrees out of phase with each other. So what do I mean by that? There we see, there we go. Okay, can we see this? Can you guys see the whiteboard?
Yep.
All right. So if we've got, oh, what's that? I think I need to actually highlight the pencil. All right, there we go. So we're going to have the waveform coming in like that with a single phase, with, let's say, this being 0 volts. And actually the two phases come in and they're 180 degrees out of phase with each other. So they don't bleed over each other, but this one would be 120 volts. This one would be 120 volts. And then in combination, they're going to be 240 volts. Does that part make sense? And this is what 90% of what you're going to be dealing with deals with. In the US, it's 240. In other countries, it may be different.
The 240 Graham is from peak to peak.
Yeah.
Is that correct, Jay?
Yeah. Yeah. 240. It's actually, it's a little bit harder to, it's the root mean square of the phase which is, because if you averaged out the voltage, it would be 0, because it goes from negative to positive to negative. So what they're saying is this is the root mean square, which is going to be 120. Now with 3-phase power, it comes in out of phase with each other, but only 120 degrees out of phase. So your 3-phase, the waveform is going to be, more like, yeah, these are really bad. But anyway, you've got three lines going across there. Now, one of the nice things about 3-phase wire or 3-phase power, if I drew it properly, is if we look at a single phase current like this, and let's say this is 0, then the number of sine waves per second is the hertz. So in America, it's going to be 60 of these waves every second. So 120 times every second, the amount of voltage going through is 0 as it goes from positive to negative to positive to negative. Well, it goes so fast, it's like a movie projector. You don't see that. You don't see that stutter, but it's there. And so it causes the vibration within larger motors because 120 times a second, it's getting no power. So 3-phase evens that out. So it never, and at no point is it 0, because as one phase is declining, the next is coming up and so on. So they tend to use 3-phase for heavy equipment like that because it will run smoother. It has better torque. It has less vibrations. So they'll run smoother, cleaner, without the same wear and tear. So that's one reason why some equipment will use 3-phase. Also, when you go to figure out how many amps are on 3-phase versus single phase, it's a little bit different because remember, watts equals amps times volts. So let me get the pen again. So if I've got this is fairly typical. Let's say I've got a 60-watt light bulb and I know I'm operating at 120 volts. So, whoops, not there, should be here. So what is my amps? So I'll ask you that, Graham. If watts equals amps times volts, how many amps would be running through that to power a 60-watt light bulb?
2.
2? All right. So we would basically, to get rid of this, we would divide each side by 120.
Yeah.
And so anyway, it ends up being 0.5.
Oh, dang it.
0.5 amps.
Math on the spot.
There you go.
Yep. No, yep. I got there though.
Yeah. So that's right. How you calculate watts equals amps times volts. And that's one of the equations, of course, that you need to know. Right. So if I wanted to know how many of those 60-watt light bulbs could I hook up before I would on a 20 amp circuit. So I've got a 20 amp breaker and I've got a bunch of 60-watt light bulbs. Well, it's telling me I could hook up 40 of them before I would reach the 20 amp limit. You know, in theory, it might pop the breaker at the 40th one. 39 would be fine. 40, pop the breaker. But in if in watts equals amps times volts, or sorry, that shouldn't be it should be an I for amps. And that's one of the weirdness of the abbreviation with amps. We use the letter I in the abstract to talk about amps for intensité de courant. But if I want to do a specific amp, I'll put like 0.5 A, because that's 0.5. I wouldn't say 0.5 I, but I wouldn't write watts equals A times V. So just part of the nomenclature. But anyway, with three-phase electricity, you do not calculate amps. It's this by straight with a 1. It's actually watts. And you don't need to know this for the test, but watts is the square root of 3 I times V for three-phase electricity. And the reason that's going to be a big deal is you can use a lot smaller wire. Okay, because the size of the wire is dependent on the amount of amps going through. And so what they're trying to do is minimize the size of the wire. So if you can minimize the amps in the circuit, you minimize the size of the wire. So if you're running three-phase electricity, you're using less amps to get the same amount of power through the wire. So all of those electric lines that are out there on the street that you see, that's all three-phase power flowing through there. In fact, it's probably at about 7,000 volts out there on those electric lines that are up there running by your street. When it gets to that transformer that's on the pole outside of your house, that's when it's converted to 240 volt single phase power that then runs into your home. And the reason for that is because by increasing the size of the voltage and by increasing and putting it in three-phase, you can use smaller wire to get a lot of power to the home. That's why when you look at those wires that are running along the side of the road, if they were 240 volt single phase, they'd have to be the size of your arm just to get the power down the street. And that'd be just too cumbersome, too expensive. So that's probably more than you wanted to know, but so all right. Any other electricity questions there, Graham?
No, I don't think so. Not related to the chapter.
Yeah. Well, if it doesn't have to be related. So
all right. There's just one. It's like a housekeeping question of: is there somewhere I can see where the schedule is of where we're meant to be week to week, which chapters we're going over?
Yeah. In fact, I sent that out to everybody with the
Okay.
system that apparently did not go out to everybody. So I'm gonna go back and re-put that together.
Cool.
But yeah, I'll send it to everybody just so that you know you're not falling behind. Also, I did get a request. Somebody was already making their hotel arrangements for the labs and the exam. And I sent him the physical address. I'll send it out to everybody as well. But it's at Melink Solar, which is in a little suburb called Melrose. It's like between Dayton and Cincinnati. And so it's a very, very nice facility. There's some hotels nearby, quite a lot, but it's easy on, easy out. So even if you're 15 miles away, you're still only going to be about 15 minutes away. So that won't be a problem, but I'll send you the exact address. I just didn't think anybody was going to worry too much about hotels this quick, but apparently some people are more organized than I am. So,
Okay.
Yeah.
Just go back to that three-phase, the 3 lines you see that hook up to the transformer. Where's the neutral?
Where's the neutral up there? Yeah, I guess the reason I'm hesitating is well, it would be running with that. I'm just trying to decide, does it require a neutral? And it does. Yeah, so the neutral wire would be with those wires coming in. Some three-phase doesn't have a neutral. Like I know
Right, so 240, well, yeah,
240 you would have a neutral.
yeah,
But like there's a delta configuration with a neutral and without a neutral for three-phase. I think Y configuration, I think it does have a neutral that's considered part of it. But now we're kind of getting into some of the stuff that's not really part of this class, because
okay.
I don't want to freak everybody out. But yeah, where that comes into play, and really with this class, the thing you need to know about three-phase, first off, that it exists, okay, that it is a thing. But secondly, when you go out to buy an inverter, oftentimes you're going to see the voltage rating on that inverter, and it might, for example, say this is a 208 volt inverter. Well, if you don't understand that 208 is a three-phase voltage, you may be buying a three-phase inverter for a single-phase installation. So you want to make sure that you're getting the right inverter for your installation. So you want to make sure you're getting a 240 volt single phase if that's what you're installing. The typical configurations for three-phase are going to be 208 120. That's between when you're talking about the voltages, the 208 is between the two of the hots, and the 120 is between a hot and the neutral. So you can run regular 120 outlets off of a three-phase system. Or there's also 480 277, which is for more industrial type three-phase systems. But for most of what we're going to be dealing with, you're going to be dealing with 240 single-phase systems. Another thing to look out for is, let's say that you're looking online and you're looking at an inverter and it says it's a 250 volt or a 230 volt system. You might be in a European website, right? Something to be aware of, because England typically talks about 250 volt. Mainland Europe usually talks about 230 volt. So you might be buying a European inverter, which isn't going to do you much good. So again, just be aware. And that's where this comes into play here.
So if they say 208, 240, that's all right to get then?
It's not going to be 208. Yeah. If it says 208, 240, it basically means that that particular inverter will either operate under three-phase or single phase.
Okay.
And most of those inverters are going to recognize what you've hooked up to and will automatically adjust to set to whatever it is that you're connecting it to. So that's one of the nice things. You don't even have to worry about that. And that's very common. So if you were to go out and buy an N-phase microinverter, for example, those are going to be 240, 208. They'll handle either three-phase or single phase.
Okay.
And that's the norm. That's the norm in the US anyway. So, Sadiq?
My question is, lab course will be 2 days and each person, right? Will be 2 days for each person.
Yeah, the on Saturday we'll do, you're talking about when we meet face to face.
Mm-hmm.
Yes, Saturday we will do the hands-on portion, and that will be a full day. Everybody in this class will participate on that day. Then Sunday, everybody again will get together. We'll do a review in the morning so that you are prepared for the examination, which we will then conduct in the afternoon. Originally in the schedule, you'll have seen 2 days for labs, but that was with the understanding we might get so many students signing up that I'd have to put half in one day, half in the other day. But we didn't have so many because I don't want to do more than 9 students in doing the labs, because you just can't get to the equipment if there's too many students. So because we only have, I think, 8 or 9 students here, we're going to be fine. So we'll just be Saturday and Sunday.
Okay, thank you.
Okay. Now, Have anybody gotten into chapter 5 yet, into the parts of the system? So that's where I think things start to get interesting. To me, chapters 1, 2, 3, and 4, it's all very foundational. It's all just kind of, you're beginning to learn a new language. You're learning how to refer to things. And now we're going to get into the parts. So chapter 5, we start looking at all the different component pieces. Why would you select one solar panel over another? Why would you select, how does a charge controller work? How does an inverter work? Why would you pick one versus the other? All of those kind of things. Then chapter 6, we get into site assessment. So this is very much a non-technical chapter where you go out and you say, okay, I'm going to do an assessment at a site. How do I go about doing that? What's the orientation? What's the angle? What are shading issues? How much sunlight? How do I determine how much sunlight is available? How do I route the wires? What are some of my issues there? Just kind of doing a complete solar site assessment. Then when we get into chapter 7, that's when we start designing the system. So you've learned the foundation. You've now determined how to size, how to assess the site. Now let's size the array, size the battery bank, size the wire. What do we hook together? How many amps are required? What's the rating for each of the components? All of these bits. So when we get into chapter 7, especially, I really anticipate that these meetings are going to be primarily working through some of the math problems, just coming up with people's scenarios. Say, okay, what would happen if I had a small cabin out in the middle of the woods of Kentucky? How would I design a standalone system for this? How would I determine how much sunlight is available? What size array would I need? What size battery bank would I need? What size wire would I need? Or I have a home in suburban Indianapolis, just a standard old grid-tied system. How would I design that? So we'll just work through as many of those kind of problems as we can do, here while we're all kind of face-to-face and able to do that. Because again, the study stuff you can do on your own, the lecture stuff. So assuming the sound works. So. Any other questions?
No, thank you.
Nope. Okay. All right. Well, I'm going to try and get that email thing fixed. And in the meantime, I'll see you guys all next Wednesday. And the same contact information works every week. So if for some reason you're not notified, you should be. But if you're not, what you got today, the email you got today, will get you in each week at 1 o'clock.
Oh, that same link. Okay.
Yeah, the same link every time.
Cool.
All right.
Okay, thank you.
Okay, take care.
All right.
See you.
Thank you very much.
Thanks.
Bye-bye.